In 1947, physicists believed they had finally conquered the atom. They had the Dirac equation, the most beautiful and complete description of the electron ever written. It predicted everything perfectly. Spin, magnetism, relativity. It was mathematical poetry. And then Willis Lamb pointed a microwave beam at some hydrogen atoms and broke physics. What he found was a tiny discrepancy, a whisper of wrongness. Two energy levels that the equations swore should be identical were not. The difference was minuscule, about 1 part in a million. Most scientists would have ignored it. But this tiny crack in the foundation threatened to bring down the entire edifice of quantum mechanics. The problem was not just that the theory was slightly wrong. The problem was that when physicists tried to fix it, their calculations gave answers that were infinite, not large. Infinite, as in, according to the mathematics, every electron in the universe should have infinite energy. That is obviously nonsense. You are made of electrons. You do not have infinite energy. Something was deeply, fundamentally broken. For years, the greatest minds in physics threw themselves at this problem and failed. The equations mocked them. Every approach led to the same place: infinity, absurdity, defeat. And then Richard Feynman did something that everyone said was impossible. He found a way to make the infinities cancel. He calculated the exact value of that tiny energy difference, matching experiment to a precision that still staggers the imagination. That calculation won him the Nobel Prize. And the method he invented to do it changed physics forever. This is the story of the Lamb shift, and it begins with an electron doing something it should not be able to do. To understand why the Lamb shift matters, we need to understand what physicists thought they knew in the 1940s. By that time, quantum mechanics had been spectacularly successful. Scientists could predict the behavior of atoms with extraordinary precision. The Dirac equation, published in 1928 by the British physicist Paul Dirac, seemed to be the final word on how electrons behave. It combined quantum mechanics with Einstein's special relativity in a single, elegant framework. The equation was so powerful that it predicted the existence of antimatter before anyone had ever seen it. When positrons were discovered a few years later, exactly as Dirac had predicted, physicists were convinced they had found the truth. But there was a shadow over this triumph, a darkness that most physicists tried not to look at directly. The darkness was this: when you tried to calculate certain properties of the electron using the full machinery of quantum electrodynamics, the theory of how light and matter interact, you got infinity. Not a big number. Infinity. The culprit was something called self-energy. An electron creates an electric field around itself. That field contains energy, and if you model the electron as a point with no size at all, the energy in that field becomes infinite. The electron, interacting with its own field, should have infinite mass. Obviously, electrons do not have infinite mass. So physicists did what scientists often do when faced with an inconvenient truth. They looked the other way. They developed tricks to avoid the infinities, approximations that gave sensible answers for practical problems. But everyone knew the theory was sick at its core. Then came Willis Lamb. Willis Lamb was not a theorist. He was an experimentalist, a man who built equipment and measured things. During World War II, he had worked on radar technology at Columbia University. After the war, he realized that the microwave techniques developed for radar could be used to probe the structure of atoms with unprecedented precision. In 1947, working with his graduate student Robert Rutherford, Lamb performed an experiment that would reshape physics. The experiment was conceptually simple: hydrogen. The simplest atom consists of one proton and one electron. The electron can occupy different energy levels, like a ball sitting on different steps of a staircase. When the electron jumps between levels, it emits or absorbs light of a specific frequency. According to the Dirac equation, two particular energy levels in hydrogen, called the 2s1/2 and the 2p1/2 levels, should have exactly the same energy. Identical. The equation was unambiguous about this. Lamb measured them and found they were different. The difference was tiny, about 1,000 megacycles per second in frequency terms, which corresponds to an energy of only a few millionths of an electron volt. To put that in perspective, it is about 1 part in a million of the total energy binding the electron to the proton. But it was real, it was reproducible, and it was not supposed to exist. Why? This became known as the Lamb shift, and it was a crisis. Why was such a small discrepancy such a big deal? Why was such a small discrepancy such a big deal? Because it proved that quantum electrodynamics, the theory everyone was using, was incomplete. And when physicists tried to complete it, to include the effects they had been ignoring, the mathematics exploded into infinity. The core of the problem was vacuum fluctuations. According to quantum mechanics, empty space is not really empty. It seethes with activity. Particles and antiparticles constantly pop into existence, exist for an incredibly brief moment, and then annihilate each other. These are called virtual particles, and their existence is a direct consequence of Heisenberg's uncertainty principle. The electron in a hydrogen atom is constantly interacting with these virtual particles. Wait, virtual photons appear and disappear around it. Virtual electron-positron pairs bubble up from the vacuum and vanish again. All of this affects the electron's energy. The Lamb shift is, in essence, the effect of the vacuum on the electron. The electron is being jostled, ever so slightly, by the quantum foam of empty space. This shifts its energy levels by tiny amounts, and those shifts are different for different orbitals. The Dirac equation did not include these effects. Why didn't? That is why it got the wrong answer. But when physicists tried to calculate these effects properly, they got infinity. The self-energy problem had returned with a vengeance. Hans Bethe, working at Cornell, made the first breakthrough shortly after Lamb announced his results. He performed what he called a dirty calculation, deliberately ignoring relativistic effects to avoid the infinities, and got an answer close to 1,000 megacycles. This suggested that the problem was solvable, that the infinities might somehow cancel or be absorbed. But how? Bethe's calculation was a hint, not a solution. The full relativistic treatment still gave infinity. This is where Feynman enters the story. Richard Feynman had been thinking about quantum electrodynamics for years before the Lamb shift was discovered. As a graduate student at Princeton, working with his advisor John Wheeler, he had developed radical new ways of thinking about how particles interact. Most physicists at the time thought in terms of fields. There is an electromagnetic field filling all of space, and particles interact by creating disturbances in this field. This is intuitive. You can picture the field like water and particles like boats creating ripples that affect other boats. Feynman thought differently. He asked a dangerous question. What if there is no field at all? In Feynman's picture, particles interact directly with each other across space and time. An electron here affects an electron there. Not through a field, but through a direct connection. The field is just a mathematical convenience, a bookkeeping device. What is real is the interaction between particles. This might sound like a minor philosophical distinction. It was not. It led Feynman to completely new ways of calculating. His key insight was this. Instead of asking what the field is doing, at every point in space at every moment, ask what paths the particles could take. Add up all possible paths, weight each one by a certain factor, and you get the answer. This is the path integral formulation of quantum mechanics. It sounds abstract, but it has a beautiful interpretation. A particle does not take one path from A to B. It takes all possible paths simultaneously. The probability of arriving at B is determined by how all these paths interfere with each other. Feynman developed this approach during and after the war, refining it, testing it, seeing how far he could push it. And then the Lamb shift appeared, and he had a target. Let me tell you about one of the most powerful tools ever invented for doing physics. It came from Feynman's peculiar way of thinking, and it looks almost childishly simple. Imagine you want to calculate how two electrons interact. In the old way of doing things, you would write down complicated equations involving fields, solve differential equations, and wade through pages of algebra. Feynman drew pictures. A Feynman diagram is a sketch. Time runs from left to right, or bottom to top. Particles are drawn as lines. Electrons are straight lines with arrows. Photons, the carriers of electromagnetic force, are wavy lines. When an electron emits or absorbs a photon, the lines meet at a point called a vertex. That is it. That is the whole idea. You draw all the ways the interaction could happen. Translate each diagram into a mathematical expression using simple rules, and add them up. This sounds almost too simple to be useful. It is not. It is revolutionary. Before Feynman diagrams, calculating anything in quantum electrodynamics was a nightmare. The mathematics was so complex that only a handful of people in the world could do it. And they often got different answers. Julian Schwinger, who shared the Nobel Prize with Feynman, developed an alternative approach that was mathematically rigorous, but incredibly difficult. His calculations filled dozens of pages. Feynman could get the same answer with a sketch and a few lines of algebra. But the real power of the diagrams was not just computational efficiency. It was conceptual clarity. Looking at a Feynman diagram, you can see what is happening. You can see the electron emitting a virtual photon, which gets reabsorbed. You can see a virtual electron-positron pair appearing from the vacuum and annihilating. The diagrams make the invisible visible. Now we come to the heart of the story. How did Feynman actually calculate the Lamb shift? The answer involves one of the strangest ideas in all of physics: renormalization. Remember the problem. When you calculate the self-energy of an electron, you get infinity. The electron, interacting with its own electromagnetic field, has infinite energy. This is obviously wrong. But Feynman realized something crucial. The infinity is not random. It has a very specific form. And when you calculate the effect of this infinite self-energy on physical measurements, something remarkable happens. The infinite self-energy affects the electron's mass. It adds an infinite contribution. But here's the key. We never measure the bare mass of an electron, the mass it would have without its electromagnetic field. We only ever measure the physical mass, which includes all the self-interaction effect. So Feynman and the others said, let us redefine things. Let us say that the bare mass of the electron is not what we thought. Let us adjust it by just the right infinite amount so that the physical mass, the thing we actually measure, comes out finite and equal to the observed value. This sounds like cheating. It sounds like hiding infinity under the rug. But here is why it works. Once you have done this redefinition for the mass, you can calculate other things. Things you did not use to fix the mass. And those calculations give finite answers. Answers that agree with experiment. Feynman and Stokes. The Lamb shift was the crucial test. Feynman's approach, using his diagrams and the technique of renormalization, predicted a shift of about 1057 megacycles per second. The experimental value was 1057.8 megacycles per second. Stop. Be nil. Think about that for a moment. A theory that seemed to give infinite nonsense, when properly handled, predicted a tiny energy difference to better than 1% accuracy. And this was just the beginning. Over the following decades, both theory and experiment improved. Today, the Lamb shift is known experimentally to be 1057.8447 megacycles per second, plus or minus 0.0034. The theoretical prediction is 1057.839 megacycles per second, plus or minus 0.06. That is agreement to about 1 part in 100,000. It is one of the most precise predictions in all of science. Let us step back and consider what Feynman actually showed. He demonstrated that the vacuum, empty space itself, has physical effect. The electron in a hydrogen atom is not sitting in nothing. It is immersed in a seething quantum foam of virtual particles. These particles affect its energy, its position, its properties. The Lamb shift is direct evidence of this. Richard Feynman had been thinking about quantum electrodynamics for years before the Lamb shift was discovered. As a graduate student at Princeton, working with his advisor John Wheeler, he had developed radical new ways of thinking about how particles interact. But there is something even more profound here. The success of renormalization tells us something deep about how physics works. In the old way of thinking, you might have expected that to calculate the Lamb shift, you would need to know everything about the electron down to infinitely small distance. After all, the infinities come from assuming the electron is a point. If it has some internal structure at incredibly tiny scales, that structure would matter. Renormalization tells us this is not true. You can make predictions about low-energy physics, like the Lamb shift, without knowing what happens at arbitrarily high energy. The infinities can be absorbed into a few parameters, like mass and charge, and the rest of the predictions are finite and testable. This is a statement about the nature of physical theories. It says that you do not need a complete theory of everything to make accurate predictions about things you can actually measure. Physics at different scales separates. What happens at energies we can probe does not depend sensitively on what happens at energies we cannot. This idea, which emerged from the struggle to calculate the Lamb shift, has shaped all of modern particle physics. The Standard Model, our best theory of fundamental particles and forces, is a renormalizable quantum field theory. The entire framework rests on insights that Feynman, Schwinger, and Tomonaga developed in those crucial years. Schwinger, Tomonaga, and Feynman all solved the same problem. They all showed how to extract finite, correct predictions from quantum electrodynamics. They shared the Nobel Prize in 1965, almost 20 years after the Lamb shift was discovered. But Feynman's contribution was unique in a way that went beyond getting the right answer. Schwinger's approach was mathematically powerful, but extremely difficult. Only the best theorists could use it. Tomonaga's approach, developed independently in Japan during and after the war, was similar in spirit to Schwinger's. Feynman's approach was different. It was visual, it was intuitive, and it was democratizing. With Feynman diagrams, a graduate student could do calculations that would have taken Schwinger weeks. The diagrams became the common language of particle physics, used by thousands of physicists around the world. In his Nobel lecture, Feynman described how he arrived at his methods. He talked about his early work with Wheeler on direct particle interactions. He explained how he developed the path integral formulation. And then he said something characteristic. He talked about making guesses. Feynman did not derive his methods from first principles in a rigorous way. He guessed at the rules, checked that they gave sensible answers, and used them. When other physicists showed that his methods were equivalent to Schwinger's more rigorous approach, Feynman was not surprised. He had been confident they would work because they gave the right physics. This is the Feynman style. Trust your intuition. Check your answers. Do not get lost in formalism. Let me offer you a thought experiment that might help clarify what the Lamb shift is really telling us. Imagine you are trying to measure the exact position of an electron. According to classical physics, this should be straightforward. The electron is somewhere, and with good enough instruments you can find it. But quantum mechanics says, no. The more precisely you try to pin down the electron's position, the more energy you need. This is Heisenberg's uncertainty principle. And if you use enough energy, something strange happens. You create new particles. The energy required to localize an electron very precisely can create virtual electron-positron pairs. These pairs affect the original electron. They screen its charge. They shift its position. The more precisely you try to measure, the more complex the situation becomes. Well, the Lamb shift is, in a sense, the effect of this complexity on atomic energy levels. The electron, in a hydrogen atom, is never entirely alone. It is surrounded by a cloud of virtual particles, constantly appearing and disappearing. This cloud has physical effects. In the 2s orbital, the electron has a chance of being found right at the nucleus. In the 2p orbital, it does not. This difference in position means a different interaction with the virtual particle cloud, and hence, a different energy. That difference is the Lamb shift. Now, you might object, if the virtual particles have physical effects, are they really virtual? Are they really different from real particles? This is a deep question, and the answer is subtle. Virtual particles are not directly observable. You cannot put them in a detector, but their effects are observable. The Lamb shift is one of those effects. The experiments confirm it. The distinction between virtual and real is not always as sharp as we might like. This is one of the lessons that quantum field theory teaches us. The vacuum is not empty. Reality is more complex than it appears. The Lamb shift was not the only triumph of the renormalization program. Around the same time, another puzzling measurement emerged. Polycarp Kush and his collaborator Foley, also at Columbia, measured the magnetic moment of the electron with extreme precision. The magnetic moment describes how the electron responds to magnetic fields, like a tiny compass needle. According to the Dirac equation, the electron's magnetic moment should have a specific value related to its charge and mass. But Kush found it was slightly larger, about 1 part in 1,000 larger. This became known as the anomalous magnetic moment, and Schwinger was able to calculate it using renormalization techniques. His result agreed perfectly with the measurement. Today, the anomalous magnetic moment of the electron is known to extraordinary precision. The experimental value agrees with the theoretical prediction to more than 10 significant figures. This makes it the most precisely verified prediction in all of physics. Think about that. A theory that seemed to predict infinities, when handled correctly, gives predictions accurate to 10 decimal places. That is like predicting the distance from New York to Los Angeles, to within the width of a human hair. This extraordinary agreement is strong evidence that quantum electrodynamics, despite its conceptual difficulties, captures something true about nature. The techniques that Feynman, Schwinger, and Tominaga developed are not just clever tricks. They reveal real physics. But we should not pass over the infinities too quickly. They are telling us something important. The infinities in quantum electrodynamics arise because we treat the electron as a point particle. If the electron had some finite size, the infinities would not appear. So why do we insist on point particles? Part of the answer is experimental. As far as we can tell, the electron has no internal structure. Experiments have probed it down to incredibly small scales, about 1/10000000th of a billionth of a meter, and found no evidence of any size at all. But there's a theoretical reason too. If the electron had a finite size, it would have internal parts. Those parts would have to be held together by some force. That force would require its own explanation. The problem would not be solved, only pushed back. Feynman was clear-eyed about this. Renormalization works, but it is not entirely satisfying. In his Nobel lecture, he did not hide his ambivalence. The infinities are swept under the rug, not truly eliminated. This is one of the reasons physicists continue to search for deeper theories. String theory, for example, proposes that particles are not points, but tiny vibrating strings. This eliminates the infinities at their source. Whether string theory is correct remains to be seen. But in the meantime, renormalization allows us to calculate, and the calculations work. Let us return to that day in 1965, when Feynman stood in Stockholm to receive the Nobel Prize. He was 47 years old. His hair was starting to gray. He had been working on other problems for years, moving on to new challenges in physics. But the Nobel Committee had finally caught up with work he had done almost 2 decades earlier. In his acceptance speech, Feynman did not take a victory lap. He told the story of how he had arrived at his ideas, starting with his undergraduate puzzlement over the self-energy problem. He described his collaboration with Wheeler. He explained his path-integral approach, and how he had guessed at the rules for his diagrams. And he concluded with characteristic honesty. "The methods work," he said. "They give correct answers. But there is more to understand." Feynman never stopped being dissatisfied, never stopped pushing for deeper understanding. This is perhaps his greatest legacy. Not just the diagrams or the calculations, but the attitude, the willingness to question everything, the insistence that understanding, real understanding, matters more than getting the right answer. The Lamb shift was measured in 1947. The theoretical explanation came over the following years. The Nobel Prize arrived in 1965. But the next and physicists are still working on the problem today, still pushing the precision, still looking for cracks that might reveal deeper physics. The current theoretical prediction for the Lamb shift includes contributions from many subtle effects, corrections from the finite size of the proton, Corrections from higher-order Feynman diagrams with more and more virtual particles. Corrections from the weak nuclear force. 1. Each contribution is tiny, but together they matter. The agreement between theory and experiment remains extraordinary. And any future disagreement, any new discrepancy, like the one Lamb found in 1947, could again revolutionize physics. That is the nature of science. Today's triumph contains the seeds of tomorrow's revolution. What does it mean that empty space is not empty? What does it mean that the vacuum seethes with activity? That virtual particles constantly appear and disappear? That these ghostly entities affect real atoms in measurable ways? It means that reality is not what it seems. The simple picture of particles moving through empty space is incomplete. Space itself is dynamic, alive with quantum fluctuations. The electron in your body is never alone. It swims in a sea of virtual particles, constantly interacting with the void. Richard Feynman loved this about physics. He loved that nature was stranger than anyone could have invented. He loved that careful measurement and honest calculation could reveal truths that imagination alone could never reach. In one of his lectures, Feynman said that the job of physics is not to explain why nature is the way it is, but to describe how it behaves. The why questions may be forever beyond us, but the how questions, those we can answer. And the answers are beautiful. The Lamb shift is beautiful. A tiny discrepancy in the energy levels of hydrogen, just 1 part in a million, led to a revolution in physics. It revealed the quantum nature of the vacuum. It forced physicists to develop new mathematical techniques. But it tested quantum electrodynamics to extraordinary precision. And it showed that nature, when examined closely enough, always has more to teach us. Freeman Dyson, who helped unify the work of Feynman, Schwinger, and Tominaga, wrote years later about the golden days when the Lamb shift was the central theme of physics. Those years, he said, were golden for all physicists of his generation. Why golden? Because the problems were hard enough to be interesting, but solvable. Because experiment and theory were engaged in an intimate dance. Because progress was real and visible and transformative. Physics still has such moments. The discovery of the Higgs boson in 2012 was one. The detection of gravitational waves in 2015 was another. Each time, decades of theoretical work meet experimental confirmation, and our understanding of the universe deepens. The Lamb shift was one of the first such moments of the modern era. And Richard Feynman, with his pictures and his intuition and his relentless honesty, helped make it possible. Look around you. The light entering your eyes, the atoms in your body, the empty space between them. All are described by the theory that emerged from those years of struggle. Every LED in your devices, every MRI in your hospitals, every chip in your computers owes something to quantum electrodynamics. And at the foundation, holding it all together, is that impossible calculation. The one that gave finite answers when everyone expected infinity. The one that matched experiment to 100,000 places. The one that won Feynman the Nobel Prize. The vacuum is not empty. Physics is not complete. And nature, as always, invites us to look deeper.